Within the next few seconds, I just looked at the national debt clock online. This is what our national debt will be. I'll just write the number. Now, when we see numbers that big, they don't make much sense to us. And when we look at things quantitatively, often we have to think about them carefully and look at other quantities, compare them to other quantities in order for them to make sense. First of all, how do you read this number? Well, if you count over, here we have hundreds and thousands, millions, 17,864,565,500,000. Well, that number is so big. Let's see, it has these, by the way, these symbols that we use to write our numbers with, the 10 symbols, 0 through 9, those are called digits. And so we say that this number has 3, 6, 9, 12, 13, 14 digits. So that's a huge number, hard to understand. But maybe you could understand it better if you Googled and found out that this number is larger than, it is greater than the GDP of the United States, the total value of everything made in a year. It is also greater than the total household income in the United States, by far. So altogether, if every single person in the United States next year gave all of their money and we lived on nothing, we still could not pay off the national debt. So thinking about numbers and comparing to other quantities helps us to understand large numbers. So we are going to be talking about ways to look at quantities, sometimes by just estimating them, and also a very powerful but simple principle called the pigeonhole principle. It's section 2.1. When you see words like this written in red, you know that these are words that you need to know how to define, actually write down what they mean, and understand them completely when we use them in class discussions. Try to use these words yourselves when you're discussing with your table mates. Use these words. The natural numbers are the numbers that we learned when we were children, the ones that we count with. And let's see, I'll make a list of them. Here is a list. And of course, I don't have room on this page, do I, to write them all because there are infinitely many. So at some point, I'll put ... That means, this here means, and so on. Forever. The and so on has to be established what we mean by what I write here. I have to get a pattern going here, and then I put ... and you know that it's 8, 9, 10, etc. This is called a list. There's another way of writing this that we'll use often. N is equal to the set containing 1, 2, 3, 4, ... I don't need to write out 7 of numbers. This is called the set of natural numbers. And so you see these are called set brackets here. The ... always means the same thing. It means and so on, continuing that pattern. And I read this sentence as capital N is the set of numbers 1, 2, 3, 4, comma, ... and so on. And this set bracket here is like a period. So we can write the natural numbers as a list. It's just different notation, that's all. But notation is extremely important in mathematics. This would be, the upper one is a list. You see there's no set brackets. It's a list, putting them in order. And down here, we're using set brackets. And so we call that a set. A set is is a collection of objects. We call those objects elements. Elements of the set. A set is a collection of objects, so we call that the set of natural numbers, and the elements are the numbers, the natural numbers. Some sets are finite and some are infinite. We're not going to actually define these words finite and infinite, but certainly you know what they mean. A finite set would be an example like the set of numbers 1, 2, and 3. There's a finite set with 3 elements in it. Or we could say the set of students in our class. There the elements are people, and there'd be 25 of them. Almost every set that we speak about in real life is a finite set, but some of them are too large to count, too large to know how many are in there. For example, here's another finite set. The set of grains of sand on a beach. Well, we know that that is a finite number of them. At any given time, there is a finite number of grains of sand. They're not infinite. But we don't know what that number would be. Another example would be the, excuse me, I'm going to use this when I want to say numbers. The number of hairs on your body. Well, we don't know how to count that. We know that there, at any given moment, there's a finite number of them. We don't have an infinite amount of hair on our bodies, but it's a very large number, and we don't know how to count it. So finite sets can be very, very large, or they can be small. And infinite sets, well, we have looked at one infinite set so far. The set of natural numbers is an infinite set. And I won't define infinite, you know what it means. It is not finite. Infinite means not finite. And finite means there is a specific number of elements in the set. In section 2.1, we would like to be able to estimate some of these very large finite sets and learn things from estimating them, even though we cannot count them. Here's an example of a problem in our textbook that we can understand better if we quantify it in different ways and think about it carefully before we decide what our answer is. Someone offers to give you $1 million in $1 bills. To receive the money, you must lie down. The million $1 bills will be placed on your stomach. Now, obviously, that is impossible, but we are assuming that it is possible to stack up $1 million $1 bills on your stomach. If you keep them on your stomach for 10 minutes, the money is yours. Do you accept the offer? Most of us would say, yeah, bring it on. But we have to consider carefully before we say that. So let's look at this quantitatively. Now remember, I realize it is impossible to put $1 million $1 bills on your stomach, but we are assuming that it is possible. So what would be another issue that would be important here? Well, we know that there's 1 million of them, but I wonder how much they would weigh. How much would $1 million $1 bills weigh? That might be something we should consider. So I Googled, and I found that one bill weighs 1 gram. I just found that online. So this implies or tells us that the money that we would put on our belly would weigh, the total weight would be 1 million grams. Well, being from the United States, we don't really weigh things in the metric system, so we don't know what 1 million grams is. So we would need to convert that to pounds in order for it to make sense to us. So I did that. If you Google, you'll find that 454 grams is equal to 1 pound. So dividing 1 million by 454, I get the total weight. Means that the total weight of the $1 million is, dividing 1 million by 454, I get approximately, and I'll use these little curly equal signs, approximately 2,202 pounds. So you have to ask yourself, do you want to put 2,000 pounds on your belly for 10 minutes? Well, I think most of you would say, no, I'm not going to chance that. But if you want, you could Google and find out, well, what is something that weighs about that? I thought of a car. In order for this to make sense to me, see, we keep quantifying, estimating. In order for this amount of weight to make sense to me and know, what is something that weighs that, I found that the 2014 Mitsubishi Mirage, so it's a small compact car, weighs 1,973 pounds. Well, then I've decided I cannot put a car on my belly and leave it there for 10 minutes. So we say our answer is no. We wouldn't take the $1 million because we wouldn't live to use it. It would smash us. The lesson here is to keep looking at things in a quantitative way, and maybe you'll have to use estimation to make sense out of a quantity. Here's another question I'd like you to consider. You might want to put these on pause when a question is posed and see if you can think about it before you listen to what I say. If you have 400 people in a room, why do 2 of them for sure have the same birthday? I don't mean year, I mean just day and month, like March 1st is mine. Why do 2 of them for sure have the same birthday? And how could you prove this? Well, hopefully you put this on pause and you know for sure that 2 of them will, and you would say because there are 365 days in a year. So if you have 400 people in a room, since 400 is a bigger number than 365, this would imply to us that at least 2 people, more than that really, but at least 2 covers all bases, at least 2 people will have the same birthday. I'll just put BD, birthday. Now, I want you to notice here this word because it's very important. I said at least 2. That means 2 or 3 or 4 Or heck, maybe all 400 of them have the same birthday. But at least 2 will. Now let me ask you a little question. I don't have room to write it, but does this mean that someone in the room has your birthday? And the answer is no. It doesn't mean that someone in the room will have your birthday. It means that at least 2 people in the room will have the same birthday. And please make sure that you understand the difference in that wording. Now this is an example of something that we call the pigeonhole principle. I'll refer to it as PHP at different times in the course, the pigeonhole principle. And let's see, I'm going to draw you a little picture and you'll never forget. It's so easy to remember this. You know, I guess they call it pigeonhole principle because pigeons live in these boxes, and there's holes that they can fly into and perches in there. So let's say that there's 4 holes in the box, the house that they live in, and let's say that there are 6 birds. Here's the birds. Now, if all of the birds fly into the box, at least 2 birds will have to fly into the same hole. It's obvious. All 6 birds cannot go into different holes. So let me write the pigeonhole principle, and I'm just going to write it in terms of using this example, and you can remember it that way. If there are more birds than holes, at least, again the wording is important, at least 2 birds will fly into the same hole. That's the pigeonhole principle. Again, think about the words. It doesn't mean maybe they'll all fly into the same hole. Some students say, well, one of these 6 birds will go here, and 1 will go here, and 1 will go here, and 1 will go here, and there'll be 2 left over. That's not what it's saying. All 6 of them could very well fly into the same hole. It doesn't mean anything about how many fly into any particular hole. We just know that at least 2 will fly into the same hole. Here's an example to illustrate the pigeonhole principle. If Greg has 50 red, 40 blue, 60 yellow, and 100 black socks in a drawer, how many socks must he pull out of the drawer to guarantee he has a pair? Well, you could answer this without formally thinking about the pigeonhole principle. You know, he could draw 4 without getting a pair. He could draw red, blue, yellow, and black. But when he draws his 5th sock, he'll have to get red, blue, yellow, or black again. So we know the answer is 5. But let's see how the pigeonhole principle applies here. 5 is the number of socks that he's going to draw, and that is greater than 4, the number of colors that are in the box. So here we're saying that the birds, in the statement of the pigeonhole principle, the birds are what we're considering socks, and the 4 represents the colors or the holes in the pigeonhole principles. We have 4 colors, so we must draw at least 5 socks in order to get a match. Here's another example. Given a set of 10 natural numbers, so there's 2 vocabulary words I hope you learned. A set, a collection of 10 natural numbers, our counting numbers. How do you know that some of them leave the same remainder when divided by 6. At least 2 of them will leave the same remainder. You have 10 numbers. How do you know that? Well, let's think about remainders upon division by 6. What are they? So if you divide a natural number by 6, you could get one of 6 remainders. If the number is evenly divisible by 6, you have a remainder of 0. Or if it's a number like 19, you get a remainder of 1. You could get a remainder of 2, 3, 4, or 5. But every natural number, if you divide it by 6, is going to leave you with one of those 6 remainders. So we have 10 numbers. We have 10 numbers. And that is more numbers than there are 6 possible remainders. So once you write this, you can just write this here. You don't have to say birds and holes. The number of numbers is greater than the number of possible remainders. So by the pigeonhole principle, by PHP, we know that at least 2 numbers will leave the same remainder. This is how you write up a solution to something like this. You show the inequality that you're using. The number of birds greater than the number of holes. Here, 10 numbers is greater than 6 possible remainders upon division by 6, and so at least 2 of them will have the same remainder. Maybe they all will, but they're not all going to have different remainders.